Look around you for a moment. I don't mean abstractly. I mean literally where you are right now. The walls around you, the ceiling above you, the floor beneath your feet. Your brain understands this space effortlessly. You don't calculate distances. You simply feel them. You know how far the door is? How many steps it takes to cross the room? How long it would take you to reach the window? This is the scale your mind was built for, the scale of survival, of movement, of immediate reality. A few meters, maybe 10, maybe 20. This is the universe. Your intuition trusts. Now let me stretch that space slightly. Imagine the entire building you're in. Every room, every hallway, every staircase stacked together into a single mental picture. Suddenly the scale expands, but still remains comfortable. You can imagine walking from one end to the other, climbing floors, stepping outside. Maybe the building is 50 meters across, maybe 100. Your mind still holds it easily, still maps it without strain. Nothing about this distance feels mysterious. It's simply larger, but not fundamentally different. Step outside in your mind. The building becomes a small object in a neighborhood. Streets stretch outward, lined with homes, shops, intersections, traffic lights. Now distance begins to stretch into kilometers, yet you still understand it intuitively because you've traveled it before. You know what 5 minutes feels like? What 10 minutes feels like? What a short drive across town means. The geography becomes larger, but still familiar, still human. You can imagine routes, shortcuts, landmarks, direction. Your mental map expands naturally, like a balloon slowly filling with air. Push further. The city spreads outward, suburbs dissolving into highways, rivers, farmland, mountains. The distances now become tens of kilometers, maybe hundreds. You can't walk it anymore, but you can drive it. You've experienced this scale through travel, through long rides, through watching landscapes change. The space is larger, but still grounded in lived experience. It still belongs to the world your brain evolved to understand. Now, stretch beyond the city. Think about your country. Thousands of kilometers from one end to the other. Landscapes change dramatically across this span. Climates shift. Cultures vary. Time zones sometimes separate one side from the other. A trip across this distance takes days, not minutes. You begin to sense size in a new way, not as something you can grasp instantly, but as something you must experience through duration. Distance becomes time. Space becomes a journey. Your intuition begins to loosen its grip. Then expand again. The entire Earth, a sphere about 40,000 kilometers around. Oceans covering most of its surface. Continents scattered like irregular islands. Clouds moving constantly across the atmosphere. Suddenly, everything you've ever known fits onto one object. Every city, every mountain, every desert, every ocean trench, every human being, every piece of history, all contained on a single planet floating in darkness. You can still describe its size numerically, but something subtle changes. Your intuition no longer feels the distance. It only understands the concept. The earth is no longer a place you move across. It becomes something you observe. And here is the quiet shift. When you stand in your room, the world feels large. When you imagine your city, the world feels vast. But when you step back and see Earth as a whole, something unexpected happens. The scale collapses. All distances you once considered enormous shrink into features on a single sphere. The longest road becomes a thin line. The widest ocean becomes a shallow curve your entire life. Every memory you have, every place you've been, exists on a surface so small it can be covered by a fingertip in a scaled model. Your mind doesn't resist this because it can't. It simply accepts the compression. The familiar world you trusted as enormous quietly transforms into something finite, contained, almost delicate. And without noticing it, you've already taken the first step away from human scale, leaving behind the distances your intuition was designed to understand, standing at the edge of something far larger, where even a planet begins to feel like a small place. Take the Earth you were holding in your mind a moment ago and place the moon beside it. This is where human intuition begins to fail for the first time, in a serious way, because the moon looks near enough to belong to our immediate surroundings. You see it often, you recognize its shape instantly. And on some nights, its surface even seems textured enough to feel familiar. But familiarity is not the same thing as nearness. The moon is about 384,000 kilometers away from Earth, which means that if you tried to translate that distance into ordinary human experience, it would stop behaving like something local almost at once. A car moving at highway speed would need months to get there. The Apollo astronauts, traveling at extraordinary speed in the most powerful machine their civilization had built, still needed about 3 days to make the crossing. That fact alone tells you something important. The nearest world beyond Earth is not nearby in any practical human sense. A useful comparison helps. If Earth were reduced to the size of a basketball, the moon would be about the size of a tennis ball, but it would not be hovering close to the basketball. It would be several meters away, across the room. That empty span matters more than people usually realize, because it introduces one of the central truths of astronomy. Space is not mainly filled with objects, but with separation. The gap between Earth and Moon is so large that all the other planets in the solar system could fit inside it, lined up side by side. When you first hear that, it sounds impossible, because the mind expects a moon to orbit close to its planet. But the actual structure is mostly distance, with two bodies placed at either end of it. Then there is the sun, which is so visually constant in daily life that we almost stop thinking about what it is. It is not simply the bright thing in the daytime sky. It is a star, and it sits about 150 million kilometers away from Earth. That distance is large enough that astronomers use it as a basic unit, one astronomical unit. Because ordinary measurements start becoming clumsy, light from the sun takes about 8 minutes and 20 seconds to reach Earth. So every sunrise is already old by the time you see it. The sunlight on your skin is not arriving from the sun as it is now, but from the sun as it was minutes earlier, even within our own solar system. Reality does not reach us instantly. The sun also dominates the solar system in a way that is easy to say and hard to feel. It contains almost all of the mass in the system. More than 1 million Earths could fit inside it. In its core, hydrogen is being fused into helium under pressures and temperatures so extreme that the process powers everything from climate to photosynthesis to the possibility of liquid water here on Earth. Yet because it is so far away, all that violence is visually compressed into a clean circle of light. Distance simplifies appearances. The same thing happens with the planets. Mercury sounds close because it is the closest planet to the sun. Yet it still orbits tens of millions of kilometers from it. Venus is often called our sister planet. But even at favorable alignment, it remains vastly farther away than the moon. Mars, the world people most often imagine visiting, is not sitting next door waiting for us. Its distance changes constantly, and even under the best conditions, it remains separated from Earth by a gulf so large that communication takes minutes, and missions require careful timing across years. Once you look at the moon and the sun in this way, the inner solar system stops feeling compact. It is not a small neighborhood of worlds clustered around us. It is a sparse system in which a few bodies occupy enormous intervals, and where even the nearest destinations already exceed the scale human life was built to navigate directly. Move outward from Mars, and something subtle happens. The inner solar system, which already felt wide, begins to thin out even more. And the next major world does not appear after a modest increase in distance, but after a jump so large that the scale changes again. Jupiter sits hundreds of millions of kilometers beyond the orbit of Mars. And when you place it mentally into the structure you've built so far, it no longer feels like another nearby planet, but like the beginning of a different region entirely. Jupiter is not just larger than Earth. It is larger than everything else combined. More than 1,000 Earths could fit inside it. And its gravity shapes the architecture of the solar system, bending asteroid belts, capturing moons, and subtly influencing the motion of objects far beyond its orbit. Yet despite its size, it is surrounded by enormous emptiness. A massive object isolated within a volume of space that would swallow the inner planets without crowding. Around Jupiter orbit dozens of moons, some of them worlds in their own right. Europa hides a global ocean beneath a shell of ice, an ocean that may contain more water than all of Earth's seas combined. Io is stretched and heated by Jupiter's gravity until its surface erupts constantly with volcanoes that throw material hundreds of kilometers into space. Ganymede is larger than Mercury and carries its own magnetic field, while Callisto preserves a record of impact stretching back billions of years. These are not small companions. They are planetary scale environments scattered around a gas giant, each separated from the others by distances comparable to the span between Earth and Moon. Even within a single planetary system, space refuses to compress itself. Beyond Jupiter, Saturn appears not as a close neighbor, but as another leap outward. Its rings stretch tens of thousands of kilometers, yet they are astonishingly thin, a structure that seems delicate despite its enormous extent. Saturn's moon, Titan, carries lakes and rivers, not of water, but of liquid methane, while Enceladus sprays jets of icy material into space from an ocean hidden beneath its frozen crust. These distant worlds are colder, quieter, and dimmer, yet they remain complex, as if the solar system continues to unfold long after the warmth of the sun has weakened. Farther still, Uranus tilts onto its side, rotating as though knocked over, its poles alternately facing the sun for decades at a time. Neptune, deeper in the dark, hosts winds faster than any seen on Earth, storms moving through an atmosphere lit by a sun that has shrunk to a brilliant star. At these distances, sunlight no longer dominates the sky. The sun becomes a bright point, still the gravitational anchor of the system, but no longer visually overwhelming. The planets out here exist in a subdued twilight, separated not only from each other, but from the intensity of the inner solar system. Pas Neptune. The structure dissolves further. Instead of major planets, there is a wide belt of icy bodies. Fragments left over from planetary formation. Pluto moves through this region on an elongated path, sometimes closer to the sun than Neptune, sometimes far beyond it. When the New Horizons spacecraft traveled to Pluto, it needed nearly a decade of continuous motion just to reach a single dwarf planet. That journey did not cross the solar system. It only entered its outer regions. Beyond Pluto, more objects drift in a sparse ring, each separated by distances that would once have seemed enormous but now feel expected. Eventually, the solar system no longer resembles a set of orbits in a plane, but expands into a vast spherical cloud of distant icy remnants. The Oort cloud, extending tens of thousands of astronomical units outward. Here, the sun's influence fades gradually, not with a clear boundary, but with decreasing pull. A spacecraft traveling outward would not encounter a wall or a final marker. It would simply move into space, where the sun becomes one star among many, its gravity no longer dominant, its presence no longer structurally defining. By the time you reach this region, the solar system stops feeling like a system at all. The planets are far behind. The sun is just another bright point, and the distances between objects are so large that the structure dissolves into scattered remnants orbiting slowly in the dark. The domain of our star does not end with a sharp edge, but with a gradual thinning, where the idea of belonging to the solar system becomes less about location and more about a faint gravitational connection stretching across immense space. Once you move beyond the fading influence of the sun, the scale changes in a way that is difficult to anticipate. Inside the solar system, distances were measured in millions or billions of kilometers, and even though those numbers felt large, they still belong to a structure anchored by a single star. But the moment you step into interstellar space, the sun becomes just another point of light, and the next nearest star is not slightly farther away, but separated by a gulf so large that previous distances begin to look compressed by comparison. The closest star system to us, Proxima Centauri, lies about 24 light years away. And that unit matters because ordinary measurements become almost meaningless. A light year is the distance light travels in 1 year, moving at about 300 kilometers per second. Fast enough to circle Earth several times in a single second. Even at that speed, light needs more than 4 years to cross the gap to our nearest stellar neighbor. This changes how distance behaves. When you look at Proxima Centauri, you are not seeing it as it exists now. You are seeing it as it was more than 4 years ago, because the light entering your eye began its journey years before it reached you. The same is true for every star in the sky. Distance becomes time. The farther away something is, the further back into the past you are observing it. The night sky is not a snapshot of the present, but a layered record of different moments, each star representing a different delay between emission and observation. Some of the brightest stars visible to the naked eye are tens or hundreds of light years away, meaning their light left before modern technology existed, before airplanes, before electricity in some cases. When you look upward, you are looking across history as much as across space. The emptiness between stars is also more extreme than most people expect. If you shrink the sun to the size of a grain of sand and place it on the ground, the nearest star would be another grain of sand several kilometers away. Nothing fills that distance in any meaningful sense. There is no glowing haze, no dense field of objects, just a near-perfect vacuum with only a few stray atoms per cubic meter. Even spacecraft traveling faster than anything humans have built would require tens of thousands of years to reach the nearest star. Voyager, launched in 1977 and now far beyond the planets, has been traveling for decades and has only begun to enter interstellar space at its current speed. It would need tens of thousands of years to pass near another star. The scale is not simply large, it is isolating. Stars themselves vary widely despite their similar appearance from Earth. Proxima Centauri is a red dwarf, smaller and cooler than the Sun, emitting far less light. Many of the stars near us belong to this category, faint and long-lived, burning their fuel slowly for trillions of years. Others are brighter and hotter, like Sirius, which appears as the brightest star in our sky, but lies about 6 light years away. Sirius is actually a binary system consisting of a main sequence star and a white dwarf. The collapsed core of a once larger star, Vega, another prominent star, sits about 25 light years away, meaning the light you see from it tonight began its journey decades ago. Each star becomes a combination of distance and delay, a point of light carrying information from another time. As more stars are considered, the sky gradually shifts from a collection of nearby lights to a sparse distribution of distant suns, separated by enormous intervals. There is no continuous structure connecting them, no dense arrangement like the planets around the sun. Instead, each star occupies its own region, surrounded by vast emptiness, with only gravity linking them into a loose galactic framework. The darkness between stars is not an absence waiting to be filled, but the dominant feature of interstellar space, where objects are so widely spaced that motion across it unfolds over millennia rather than years. At this stage, the sky no longer behaves like a ceiling dotted with lights, but like a deep volume, where every visible point marks a different distance and a different moment in time. The stars remain steady to the eye, yet what you are seeing is already outdated, and what is happening there now is unknown. The constellations look fixed, but they are temporary alignments of objects moving slowly through space, their shapes changing over tens of thousands of years. The stillness of the night sky is therefore deceptive, not because the stars are close, but because their distances are so vast that their motion and their present state are separated from you by years, decades, or centuries of travel carried entirely by light. If you keep widening your view beyond individual stars, the sky begins to change character again, because the scattered points of light resolve into something larger, structured, and unexpectedly complex. Some of the faint smudges visible in dark skies are not single stars at all, but nebulae, vast clouds of gas and dust spread across light years of space. The Orion Nebula, for example, is not simply a fuzzy patch in the constellation Orion, but a stellar nursery more than 1,000 light years away, where gravity is slowly gathering hydrogen into dense knots that will ignite as new stars. Inside such regions, hundreds of young stars form together, surrounded by disks of material that may eventually become planets. What appears as a dim glow to the eye is actually a region of active creation, spanning distances so large that entire solar systems would fit inside it thousands of times over. Other nebulae tell different stories. The Crab Nebula, located thousands of light years away, is the expanding debris of a star that exploded nearly a millennium ago, an event bright enough to be recorded by observers on Earth in the year 1054. At its center sits a neutron star, the collapsed core of the original star, spinning rapidly and emitting beams of radiation like a cosmic lighthouse. The material surrounding it continues to expand outward, carrying the elements forged in the star's interior into space. These remnants become part of the interstellar medium, mixing with other gas clouds, eventually contributing to the formation of new stars and planets. The life cycle of stars unfolds across these enormous structures, linking creation and destruction over spans of millions of years. When you step back even further, the individual stars and nebulae merge into a broader structure, the Milky Way galaxy. On a dark night, the Milky Way appears as a pale band stretching across the sky. But this faint glow is actually the combined light of hundreds of billions of stars. Our galaxy spans roughly 100,000 light years from one side to the other, meaning that light traveling at the fastest speed possible needs 100,000 years to cross it. The sun sits not at the center, but in one of the spiral arms, about 26,000 light years from the galactic core. From our position inside the disk, we see the galaxy edge on, which is why the stars appear concentrated along a band rather than evenly distributed. At the center of the Milky Way lies a region unlike anything encountered so far. Stars orbit there at tremendous speeds, tracing paths that reveal the presence of a supermassive black hole known as Sagittarius A*. This object contains the mass of millions of suns compressed into a region smaller than the orbit of Mercury. It does not shine directly, but gas falling toward it heats to extreme temperatures and emits radiation before crossing the event horizon. The black hole influences stars thousands of light years away, shaping the motion of the inner galaxy while remaining invisible except through its gravitational effects. Its presence is not dramatic in the sky, yet it anchors the structure of the galaxy in a quiet and persistent way. The Milky Way itself is not a dense swarm of stars packed tightly together, even inside the galaxy. The distances between stars remain vast. Our Sun orbits the galactic center at roughly 220 kilometers per second. Yet one full orbit takes about 230 million years. During that time, continents drift, species evolve, and entire eras of life appear and disappear on Earth. The motion is continuous, but the scale is so large that it unfolds beyond human perception. The galaxy rotates slowly, its spiral arms shifting gradually as stars move through them. From this perspective, the sky becomes less about isolated lights and more about membership in a larger system. The Sun is one star among hundreds of billions. The solar system, a small structure embedded within a spiral arm, and that arm, only one feature of a galaxy spanning distances measured in tens of thousands of light years. The Milky Way is not visible to us as an external object because we are inside it, surrounded by its stars and gas. Looking outward through its disk, the faint band of light across the sky is therefore not something distant, but the interior view of the structure we inhabit. A reminder that even the nearest stars are part of a far larger arrangement whose full shape can only be understood by stepping back in imagination rather than in space. When you finally step outside the Milky Way in your imagination, the first thing that appears is not emptiness, but another galaxy, faint and distant, yet enormous in reality. The Andromeda galaxy is about 5 million light years away, which means the light reaching us tonight left that galaxy long before modern humans existed. What looks like a small blur in the sky is actually a spiral system larger than our own, containing perhaps 1 trillion stars. If our eyes were sensitive enough to see its full extent, Andromeda would appear several times wider than the full moon. But distance compresses it into a faint patch. Even so, it remains the most distant object visible to the naked eye. A reminder that galaxies themselves can be seen across millions of years of light travel. The Milky Way and Andromeda are not isolated. They belong to a small collection known as the Local Group, a loose gathering of more than 50 galaxies bound together by gravity. Most of these are dwarf galaxies, far smaller than the 2 dominant spirals. Drifting slowly through space, while orbiting the larger systems, the distances between members of the Local Group are measured in hundreds of thousands to millions of light years. And yet even this structure occupies only a small region compared to what lies beyond. The Local Group itself is part of a larger concentration called the Virgo cluster, a collection of thousands of galaxies spread across tens of millions of light years. From this distance, individual galaxies become points within a larger swarm, each containing billions of stars, yet appearing as a single luminous object. Clusters of galaxies do not fill space uniformly. When mapped on the largest scales, they form filaments and walls surrounding enormous voids where few galaxies exist. This arrangement is known as the cosmic web, a structure extending across hundreds of millions of light years. Galaxies gather along these filaments under the influence of gravity. While the voids between them expand and empty over time, the universe on this scale resembles a network with dense regions connected by strands of matter and vast regions in between that contain almost nothing. The Milky Way, the local group, and the Virgo cluster all lie within one of these larger patterns, part of a supercluster spanning hundreds of millions of light years. At this point, distance begins to interact with another effect, the expansion of the universe. Observations show that galaxies are moving away from each other, not because they are traveling through space in the usual sense, but because space itself is stretching. The farther a galaxy is, the faster it appears to recede. This relationship, first measured by Edwin Hubble, reveals that the universe is not static but evolving. Light from distant galaxies is stretched along with space, shifting toward longer wavelengths as it travels. The farther the light has come, the more pronounced the shift becomes, allowing astronomers to measure distance through the expansion itself. This expansion has a consequence that changes how the largest scales are understood. Some galaxies are so distant that their light has been traveling for billions of years. And during that time, space has expanded significantly. The observable universe, therefore, extends much farther than the simple age of the universe might suggest, reaching tens of billions of light years in radius. Beyond that distance lies a horizon, not a physical boundary, but a limit to what light has had time to reach us since the beginning of cosmic expansion. Everything we observe is contained within this region, while beyond it may lie additional galaxies forever, beyond detection. Seen from this scale, the Milky Way becomes one galaxy among many, the local group, one cluster among countless others, and the cosmic web a pattern extending far beyond any single structure. The expansion of space gradually separates these regions, increasing the distances between clusters over time. The universe does not appear as a fixed arrangement, but as something continuously changing, with galaxies drifting apart while gravity gathers matter locally into clusters and filaments. The result is a structure both connected and expanding, where enormous systems form while the overall scale continues to grow, and where even the nearest galaxies are part of a pattern that extends far beyond the range of direct observation. When the expansion of the universe is taken into account, the idea of distance becomes inseparable from time, and the largest structure we can meaningfully describe is the observable universe itself. Light has been traveling since the early moments after the Big Bang, and because space has continued to expand while that light moved, the region we can observe today extends far beyond what a simple calculation might suggest. The observable universe has a radius of roughly 46 billion light years, meaning that the diameter of everything we can potentially see is about 93 billion light years across. Within this volume lie an estimated 2 trillion galaxies, each containing billions or trillions of stars, and around many of those stars orbit planets. The numbers grow so large that they stop behaving like quantities and instead become background conditions, a reminder that what we experience locally is only a tiny fraction of a much larger reality. Looking outward also means looking backward. Light from the moon shows it as it was a little over a second ago. Sunlight arrives 8 minutes after leaving the solar surface. The nearest star appears as it existed years ago. The center of the Milky Way is seen tens of thousands of years in the past. The Andromeda Galaxy appears as it was millions of years ago. At greater distances, entire galaxies are observed as they were when Earth did not yet exist. Eventually, observations reach the cosmic microwave background. Radiation released about 380,000 years after the Big Bang, representing the oldest light we can detect. In this sense, the observable universe is not just a map of space, but a layered record of time, where different distances correspond to different epochs of cosmic history. The deeper we look, the younger the universe appears, with so many galaxies and stars. The possibility of life elsewhere seems almost unavoidable. If even a small fraction of planets develop biology, and a smaller fraction still produce intelligent civilizations, the universe should contain many such societies, yet no clear evidence of them has appeared. This tension is known as the Fermi paradox, framed by a simple question: if life is common, where is everyone? One possibility is that intelligent life is rare, requiring a chain of unlikely steps that seldom occur. Another is that technological civilizations do not last long enough to spread far beyond their home systems. Distance itself may also be a limiting factor. Even traveling at the speed of light, communication across tens or hundreds of light years would take generations. Signals weaken as they spread, and the time required for exchanges becomes measured in decades or centuries. The vastness that allows many worlds to exist also separates them. From this perspective, the observable universe is both crowded and quiet. There may be countless planets, yet the distances between them impose isolation. Civilizations could arise, develop, and disappear without ever overlapping in time or reaching one another. The night sky, filled with stars, does not guarantee contact, because those stars represent enormous separations in both space and history. Even if other intelligent beings exist, they may lie far beyond any realistic exchange. Their signals lost in the background of natural cosmic radiation or arriving long after their sources have changed. Within this scale, Earth occupies a modest position. It orbits an ordinary star in one spiral arm of a typical galaxy, itself one among trillions. Nothing about this location appears central or structurally significant, yet this small environment supports conditions that allow matter to organize into living systems capable of observation and reflection. The atoms forming these systems originated in earlier generations of stars, distributed through nebulae, incorporated into planets, and eventually assembled into biological structures. In that sense, the same processes shaping galaxies and stars also produce the materials necessary for life. The observable universe, therefore, provides both context and contrast. On one hand, it emphasizes how small any single world is compared to the whole. On the other, it shows that complexity can arise within localized regions despite the surrounding emptiness. The light reaching us carries information across billions of years, and the ability to interpret that information exists on at least one planet. The structure of the cosmos extends far beyond direct experience, but understanding emerges locally, shaped by observations made from a narrow vantage point inside a vast and evolving universe.